I know Mark doesn't need much introduction, but I'll still do a quick brief one. I think it's all of our chairs a great pleasure and to have Mark here to give this wonderful keynote today. I think a lot of you probably already know some of his stellar work, even like these are, he has done a lot of, but two things I can already know without even checking out his bio. He co-created this area of search-based software engineering, and I am aware of his Sapiens work, have made not only research advances, but also industry, great industry, practical impact. So without further ado, I'm really excited to hear this keynote.
Thank you very much. Sorry for interrupting, and thank you for that generous welcome introduction, and thanks to all the chairs for inviting me to speak today. So yes, so I'm Mark Harman. In the next hour, we're going to be talking about scalability of genetic improvement and automated program repair. I tend to think of repair as and genetic improvement somewhat similar, especially if we're using search-based approaches to tackle them. So forgive me if I tend to sort of use the two interchangeably. I hope by the end of the talk, you'll be convinced that there's lots more we can do with repair. And in particular, we can start to actually think of perhaps a slightly more general form of repair where we're actually building new features onto systems using all the technology that you know and love from program repair. What I'm going to be talking about today is when I say it's joint work, what I mean is that a lot of the ideas I'm going to be presenting have been created in partnership with these wonderful people I list below, and I may have forgotten to list everybody, but I want to stress that the opinions I give today about repair and future directions are my own thoughts and not necessarily shared by this or by my company. Everything I say has been inspired by the work I've done with these wonderful people. So in today's talk, we're going to briefly, I'll set the scene and give you a little bit of context on my experience with repair in industry as well as in academia, and I'll look particularly at the through the lens of where the scalability challenges are, and they're not always exactly where you think they might be. So I hope that will be helpful. And in particular, what I want to then focus on is what I call the build effort problem for genetic improvement, and it's also for program repair. And without stealing my own thunder, what I mean by the build effort problem is if it takes you 20 minutes to build the system under test, then that's going to be a significant challenge for any of these automated techniques. And the idea that we can essentially sample from the space of candidate repairs. And there are ways to solve this problem, so it's not insurmountable, but it's one that I think hasn't received enough attention. And another thing that I think is an opportunity and a problem, a research problem, is this new feature build cost problem, which I'll look into. And briefly, the idea here is that when developers are thinking about a new feature, there's a significant cost to building it. And if that feature can interact with other features that we're planning to build, then there's a significant cost that's particularly pernicious if we imagine we're going to build them first and then discover the interactions only at the end and realize we can't deploy because of those interactions or significant rebuild is needed. And here is where genetic improvement and program repair can really help. And I'm going to look a little bit at how we've used simulation and something called mechanism design as our approach to repair and genetic improvement at the company Meta, in particular working on products like Facebook and Instagram. And I'll give you some results and some future directions from that. And I think these techniques we've developed them with a view to improving the systems that we're trying to test and design. But I believe that the same techniques would apply for repair if you're thinking that you're just wanting to fix bugs. So let's just start by thinking about scale challenges. So in software engineering, any technique that we develop is going to be really stress tested when we try to deploy it in practice by the challenges of scale. So one of the excitements, but also challenges for me of moving from academia into industry 5 years ago, when I joined the company Facebook, was the enormous scale of the deployment of Facebook infrastructure. So currently, nearly 3 billion people worldwide use these products. They're probably some of the most widely used software ever created by our species. And in software engineering terms, what that means is that we have incredible challenges of scale in terms of how how fast we're having to respond if we're building an infrastructure that is ingrained into the continuous integration system and that is going to be trying to test and repair changes that developers are landing into that system. So to give some concrete numbers for that, we're getting over 100,000 commits per week into our core infrastructure from many thousands of developers around the world. And that scalability challenge was the one that I anticipated would be the hardest one to tackle when we came into the company and wanted to deploy the technologies we've developed in academia. But I was wrong. And I was wrong because most companies like Meta, I'm sure it's true of the other tech companies as well, in fact I know it is, have incredibly powerful and well-developed and advanced cloud infrastructures to support their software engineers. And so although it's true that we have 100,000 commits coming in per week, which, you know, on the challenge side of the scales makes a huge scalability challenge, on the other side of the scale, we also can deploy thousands of emulators on which we can test those changes, and we can elastically scale that as well. So as we have higher times when developers land more changes, we can respond to that. So actually that turned out not to be such a scalability challenge. And with these many emulators deployed, we were able to deploy our search-based testing technology, Sapiens, relatively quickly. Within a year, we had it running on all of the principal apps that were deployed by the company. And this is what it looked like. And this was one of the great joys of my life, was this picture, because here we see the research on search-based software testing running in practice on real systems of tens of millions of lines of code used by, at the time, I think it was about 2 billion people around the world. It really felt like we'd managed to tackle scalability, deploy our research on search-based testing, and get real value to people who are relying on this technology for communications, for staying in touch with people, for social interaction, and so on. And we were so excited, we actually wrote a paper about it. So if you, rather than me going on at great length about the experience, I'd just say if you want to know more about how we deployed the search-based testing technology Sapiens, then it's in this paper, which appeared at SSBSE in 2018. But what about repair? So around the time that we got the testing technology deployed, we thought, well, wouldn't it be great if now that we can automate testing, if we could also get some of these wonderful ideas from academia into industry in terms of program repair. So I was very fortunate to have some really wonderful people in the team. In particular, there was Yue Jia and Ke Mao, with whom we formed the startup that was acquired by Facebook, and how we ended up there in the first place. Also, very soon to join the team and take a leading role was Nadia Al-Shawan, excellent PhD student. All these people all still in the company. And then the fourth one who joined the company from academia into industry was Alex Marginian. And I just want to focus a little bit on Alex because he joined the company initially as a PhD student, and he worked on a project called SapFix, which was to take our Sapiens testing technology and add automated repair. So find the bugs automatically and fix them automatically. And he did this as an intern. So he was still a PhD student at UCL, and he did a 12-week internship at Facebook, working on deploying ideas from his PhD, which was on code transplantation, but applying them specifically to program repair. And the reason I want to highlight this is because I think it shows how, as an intern, you can go into a company like Meta, as it is now, Facebook, as it was when Alex joined, and you can deploy ideas from your thesis very quickly because of this incredible infrastructure that's in place that allows you to scale up your approaches really fast and in a kind of automatic way. And then you can get results from the application of those ideas to real systems really quickly. It used to take 12 to 15 years for ideas to get from academia into industrial practice. But if you do a PhD internship at a company like ours, then you can get your ideas into practice within months by the time you finish your internship. And that makes another excellent chapter for your thesis. And it can have tremendous, profound impact on the people who are using these systems. So let me just give you an illustration of that. If you've used any of these products, perhaps you can click one of the emojis that will one can be anyone you like, happy or sad, but as long as there's some reaction. So if you've used either the Messenger app, the Facebook app, or the Instagram app on either an iPhone or an Android phone, if you could just either say hi in the chat or indicate in some way. I don't have any way to actually see, since we're not in a physical conference, I can't see your hands up, so I don't know how many it is. But my estimate, based on and overall statistics globally, is there would be somewhere between a third and a half of the people in the audience. Now, all of those people, if they take their phone out, holding in their hand a phone on which software is deployed that has been automatically tested using search-based testing techniques, and for which some of the bugs which were found by that testing technique have been automatically fixed using search-based program repair. And that last piece was done entirely by Andrew during his internship at the company. So he's able, in his PhD, to say he's had impact on nearly 3 billion people worldwide, and that he has a 50-50 chance when he goes to a conference of bumping into somebody who's running software that his own technology has improved and repaired. And you can't really beat that kind of feeling of impact. It was a tremendously successful project for us. We were very excited by the results. We published a paper on it, which I'll point to in a minute. And the other thing that excited me about it was we were able to combine Sapiens for testing with Infer for static analysis. So we already had deployed Sapiens to deploy automated search-based testing, but also already in the company, somewhat earlier than Sapiens, a group of researchers led by Peter Ahern and Dino Di Stefano, Cristiano Calcano, had deployed the Infer technology. And Infer is a static analysis that finds likely bugs using a variety of static analysis techniques based on separation logic. So these two really complement each other, because Infer essentially points to lines of code and says there's probably a bug here, whereas Sapiens runs the code and says there's a failure that's definitely happened on this emulator, and this is the line that seems to be causing it. So if those two technologies both point to the same line of code, then you've essentially got a dynamic and a static analysis agreeing on the likely point at which a bug has been caused. And this is like a kind of laser sharp fault localization technique. It helped us raise the fix rate when we combined these technologies from something between 58 to 75% to 94%, because we gave the developers such a strong signal about exactly where the bug was. But in terms of automated program repair, it also meant we could discard a whole lot of candidate repairs immediately and focus in on those that Infer and Sapiens had agreed on as the likely cause. So I haven't got time to go further into the details of what we did with SAPFix. There is a paper about it published at ICSE a couple of years ago in the Seek track, SAPFix, automated end-to-end repair at scale. I believe at the time this was the first full-scale industrial deployment of repair anywhere in the software industry, which is something I'm particularly proud of. But in particular, I'm very pleased by the more social results we're able to gain on like how developers react, because I wouldn't claim that what we did is state of the art in terms of the kinds of repair we perform. In fact, we only fixed null pointer references, so we picked the most prevalent of bugs, but also the easiest to fix, arguably. But what we did find that's interesting was the way developers react when you deploy repair. And that's all covered in some detail in this paper. And I'd encourage you to have a look at that to get some insights on how developers react when faced with these exciting repair technologies. I mean, to whet your appetite, they were very excited. A number of them were actually then deployed, the fixes. Interestingly, although 50% of the fixes were definitely semantically correct, of those 50%, the developer still commandeered the changes and rewrote the change for 50% of those. So of the half that were fixed by the technology, half landed as is, and the other half were retweaked by the engineers. And that's a very interesting phenomenon. It shows that developers do want to take ownership of how the code is written and not just what it does. Anyway, lots more insights in the paper. Plenty of time to discuss it afterwards as well when I finish the talk. But what I really want to move on to now is the scaling challenges that still remain for program repair and genetic improvement. And I'm going to take you briefly through the paper that I wrote to accompany this keynote, just to point out a few things that I don't have time to cover in great detail in this talk, but I really would love to interact with people on if they read them in the paper. I'm very happy to take comments and discussion. If you're watching this on YouTube after the keynote, then please feel free to reach out by email. We can chat about them. So the first thing I want to point out is that scale isn't always a bad thing. So we think of scale in software engineering research terms as a challenge. You know, oftentimes referees will reject a paper on the grounds that it doesn't seem to be scalable. In program repair terms, I want to encourage you to think of scale also as an opportunity. So one of the advantages of scale is that we have a huge amount of production data available that you can use to guide your testing. So as well as the fact that many systems that are of large scale have huge repositories of test cases on which you can rely, there's also all of the data from production. So for example, if you're trying to repair a performance bug, or in genetic improvement terms, if you're trying to improve the execution time, you may have a wealth of execution time data available to you to help guide whether your repair is actually performing well or whether it's regressed. So the scale also brings with it a huge amount of data, and if you're using a search-based approach, that data essentially is your fitness function guide. So that's one advantage. There's a second advantage, which is once we get above a certain scale, human intuition breaks down. So software engineers can deal very well with many of the benchmark repair type candidates we might consider on relatively small programs, the kind of systems where a developer can get the whole system into his or her head and can understand how it works. Developers can usually outperform software for improving and fixing those kinds of programs. But once we have systems of hundreds of millions of lines of code across a full stack that uses multiple different languages and technologies, there is no developer in the world, no matter how clever, who can cope with that scale. However, our automated techniques can still cope at that scale, especially if they're deployed into an infrastructure like the ones I've described. So scale is an opportunity because it gives us a wealth of data to guide the search, and because it's at that kind of scale that our technologies for improvement, our automated approaches, can really outperform humans. So if we can get our techniques to apply at that scale, that's where we're going to have the maximum impact and the maximum surprise and value over human software engineers. So the other thing about scalability challenges, I talk about in the paper, we already have many techniques at our disposal to help us scale things like program repair. One in particular that's just starting to be looked at is all of the work that already exists on optimization of test execution. So for many years, there's been research on how you would take a large pool of test data and either prioritize or select or minimize that test suite. That's been designed by humans, and it's all human-generated tests, but it all equally applies to either machine-generated tests and to tests which are being used to guide repair and improvement of software systems. So we can reuse a lot of this work. I think people have just started to work on this. But there is a challenge that I think we don't often talk about in the repair community. At least I haven't seen it talked about a lot, and that is what I'd like to call the build effort problem. So that is, if it's going to take me 20 minutes to build the system under test, then if my approach has at its core the idea that I can make hundreds of thousands of different candidate improvements and just use automation to weed out the 99,000 that are no good, that's not really going to work if each time I need to evaluate one of those, the test execution time is completely eclipsed by the build effort to create an executable version on which to test. So there are a number of techniques in the literature that already can be used to tackle this and that have started to find their way into repair work. So for example, techniques associated with mutation testing, where you're faced with a very similar problem. In fact, mutation testing is in every sense the jewel of repair, and techniques that are guided at tackling the cost of build for mutation testing will apply in repair. But there's another problem, and it's a different kind of build, which is the new feature build cost problem. So here the problem is, I'm a software engineer and I want to build this new feature which I think is going to be good, and across the way I've got a colleague who also wants to build a feature, and we both think our feature is going to be great, and we build these features, put them in the system, and then they interact in some way we hadn't really anticipated, and now neither of our features is really doing what we expected, and we have considerable further engineering work to do to try and make, to deal with the feature interaction problem. That's a sort of particularly pernicious example of the new feature build cost problem, but in general, the problem is it may be non-trivial engineering effort to build a new feature, and I'd love to be able to test how that new feature would behave and test different permutations of what I might build ahead of time. So we can think of this as a kind of speculative requirements where we could mock up some version of the system with the new feature and investigate how will that feature behave, how will it interact with other features that already exist and which we might build in future as well. And where these new features are expensive to build in terms of engineering effort, wouldn't it be great if we could have some kind of approach that would automatically scaffold up mock implementations and execute them, and then try and find the ideal parameter choices that would mean they interact in optimal ways, so that then when we do build them, we save a lot of that time. And genetic improvement is a technology that's so well geared towards solving this problem. I talk about 3 other problems in the paper that I think are related. So software specialization is a kind of case of the special case of that new feature build, and we're trying to essentially specialize the software for an existing feature. The hotfix problem, which is where there are a whole bunch of things that could go wrong with the system, and we don't necessarily know which one's going to happen next. But when it does, we want to have a repair ready to deploy. We don't want to have to go away and repair once we've, after the effect. We want to have repairs for problems that haven't yet happened, so we can hotfix them straight away. Now here we see the nexus of predictive modeling, program repair, and software testing. So we can use predictive modeling to get good educated guesses about what kind of things might go wrong, to recognize the early symptoms, and then to deploy hotfix patches preemptively to head off problems before they occur. And this is another underexplored area which I think could be very exciting. And finally, there's automated acceptance testing. So here the problem is, well, ultimately, once I've got my repair or my genetic improvement, I want to give it to the developers, and they're usually the last gatekeeper before we can deploy, and rightly so. There has to be oversight and human accountability for anything we deploy. But we can't just rely on the human engineer to sort of run loads of things and end up rejecting lots. If the acceptance test fails many times, then the human engineer will quickly discard this candidate technology. And I talk about this in more detail in the paper. I don't want to labor the point here, but we still haven't really got to a place where we can do a kind of likely automated acceptance test prediction, where we would really run what we might call a true end-to-end test that really simulates what the effect of this change will be on the real system in production, and therefore act as a kind of final gatekeeper before we then pass to the human engineer. And we really need to get that false positive rate down in order to get the engineers to accept these technologies. So that's an important problem. But in this talk, I want to focus on 2 of those problems, the build and the new feature build cost problem. The problem is, well, it may take 20 minutes to compile my program into an executable, and that's a big bottleneck for something like an automated repair technique. And the new feature build cost problem is, well, before I've even built a new feature, I want to be able to somehow use genetic improvement to experiment with it. And I want to tell you how we've used simulation as a way to tackle these 2 problems at Meta. So when I say simulation, you might think, simulation, isn't that kind of a bit like, where I make those models of reality, and it's all a bit make-believe. Some of us might have built models of planetary motion, and there it works quite well because they're governed by very simple laws of gravitational attraction, and you can do quite interesting simulations. But can it really work for complicated systems? And I really want to get the point across that simulation has developed a hell of a lot in the last decade, and the technologies that are now used for simulation are incredibly powerful and accurate. And a lot of the recent research is focused on what's called digital twins. So the idea here is that you have a software system that is a model of the physical system. So to pick a particular physical system, let's pick cars, because autonomous vehicles are a very interesting use case of simulation. So we're building a twin of, say, some aspects of the engine performance. So essentially, we do have a model of the behavior of the real physical system, the car in this case, in our software system. That's our simulation. And we have feedback from the real system to inform our simulation, to help us tweak it, make it work better. And of course, the ultimate idea is that we're building the simulation in order that we will inform the design of the car. So we might say, well, this engine doesn't perform very well under these circumstances, these road conditions, so we need to tune it in certain ways. That feedback loop, traditionally, for most of the history of simulation in our discipline, has been a human-mediated process. So we will spend some time building the simulation, going up the arrow. We will get results from the simulation, then go down the arrow and use those to inform the engineering designs. It's quite a slow iterative process, might have taken months, even years. Suppose we make it automatic. Suppose the car, as in production, is giving signal directly to the simulation, and the simulation is itself then making recommendations directly to the physically deployed engineering artifact, the car in this case. So that loop is now entirely automatic. Then what we have is a digital twin. The difference between a simulation and a digital twin is essentially this, whether this feedback loop is automated or not. If the feedback loop is entirely automated, then what you have is a digital twin of the physical engineering artifact, as opposed to just a pure simulation. So it's a special case where you have automated feedback. And it's a cyber physical digital twin, because on the top we've got a cyber system, and on the bottom we've got a physical engineering artifact, a car. The same thing applies if it's a chemical plant where you have a physical artifact, or if it's an underwater oil terminal, all of these kind of things. You've got a physical engineering artifact or power plant or system, and you've got a cyber simulation, but the two are informing each other. You have a cyber physical twin. And then you can deploy your cyber physical twin inside the engineering artifact itself, and then they really do become twins. But key here is that it's a cyber physical digital twin. What happens if, as software engineers, we both become the producer and consumer of this idea? So we say, well, I want to build a digital twin of an engineering artifact, but the engineering artifact is itself software. Now we have a special case of digital twin. And our system that I'm going to tell you about at Facebook, called DubDub, is such a system. It's a cyber digital twin, because the simulation and the thing we're simulating are both software systems. And that has a powerful ramification, which is we can make a cyber digital twin of the engineering artifact. So now we have a cyber digital twin of a cyber digital twin. Sounds like it's just an intellectual game, but it's not, because what we get is a hierarchy of digital twins where each one is simulating the other and is informed and informing the behavior of its twins. And this hierarchy allows us to explore and exploit classic engineering trade-offs between precision and speed. So as we move up the hierarchy, our digital twins might become more and more abstract, faster to compute their simulations, but less faithful in their predictions to the thing they're simulating. But because it's a hierarchy, we can essentially have a V model of testing that will make sure that these digital twins do give sufficient fidelity in the predictions that we manage that trade-off between precision and speed. So when we move to cyber digital twins, we for free get a recursive hierarchy of digital twins that allows us to trade off precision and speed. And we've talked about this a lot in a paper I'll point you to at the end, but right now I want to focus on how we could use that whole approach to help with genetic improvement and repair. So I'm going to spend 10 or 15 minutes telling you about that, and then I'll stop and take questions, because I realize that I'm covering quite a lot of ground. So far, what we've seen is that there is this problem that building a system, if it takes 20, 30 minutes build time, that's a big bottleneck for repair and genetic improvement. And many of the large-scale software systems, not just in Meta with Facebook infrastructure, but also companies like Google and so on, have reported in the literature that this is the kind of build time they face. And if we look at the history of build times back into the 70s, the largest systems we currently have to deal with always seem to have a build time of around a half an hour at least. It's almost like like one of these bizarre constants of software engineering. You know, like, yes, the technology for building improves, and we have incredibly brilliant caching strategies that allow us to do faster builds. But then what we want to build, you know, increases in its complexity and scale, and so we end up with this kind of arms race, which leads to an overall constant for the build time for the largest systems. So this is the build problem, and simulation can help us overcome it. Simultaneously, simulation can help us deal with this new feature problem. So what we've built at Facebook is a simulation of the entire Facebook platform. So we're simulating the processing elements and the databases, but we're running on the real infrastructure, but what we're simulating is the user behaviors on that infrastructure. So we have a bunch of bots, and the bots simulate user interaction. So the actions the bot performs and the observations the bot makes are all made on the real infrastructure. If one bot sends a message to the other, it goes through exactly the same stack of code as if you and I were sending. And so what we can do now is we can reward these bots in a reinforcement learning sense, for example, for bad behavior. So we can essentially encourage the bots to behave badly so that we can then explore bad behavior on the platform using bots. So it's like a safe sandbox environment in which to explore things that can go wrong, you know, harmful behavior. I want to stress that any and all of the interactions between these bots are confined to the dub platform. So although they're running on the real infrastructure, they're in a safe walled garden. We talk about this in a paper which we published at the GI workshop a couple of years ago. We call it web-enabled simulation. So I want to show you how web-enabled simulation can help tackle harmful behavior like scamming and spamming and so on. And I want to show you how we could use the simulation to overcome the problem of build times, because instead of recompiling the system, all we need to do is essentially change a simulation layer, which we call the mechanism design layer. So in particular, in our company, when we're dealing with these kinds of potential harmful behavior online, detection is much better than prevention. Excuse me, I'll say that the other way around. Prevention is much better than detection. If we think about these kinds of behavior, we really don't want them to happen at all. We want to prevent them from happening if we can. We don't want to first detect them and then have to remove the account, and then we're kind of dealing with the problem after it's occurred. So prevention is much better than detection. I want to illustrate with an analogy from driving why this is. So suppose you're driving along a nice spring day like today, and enjoying the road and scene, and suddenly a car shoots past, nearly knocks you off the road. And you're thinking, like, that's crazy, that's not allowed, and shouldn't be doing it. What kind of technology can we deploy to help with that? Well, as the designer of the platform, the road in this case, we can design two kinds of approach. We can have a detection-based approach where we deploy a speed camera, and the speed camera is going to automatically trigger when a car speeds, and therefore we're going to detect that behavior. Maybe we can then issue a fine. Or we could have a prevention technology where essentially we change the infrastructure itself. We put in speed humps that will make it harder for somebody to actually achieve that harmful behavior. It's harder for them to speed. in the case of the physical engineering material of roads, this doesn't work so well as we might hope. For a start, in the UK, this is the color we paint speed cameras. They're painted bright yellow like this because although it's a detection technology, we'd like it to be preventive. We'd like for people to see the speed camera and slow. When we deploy the prevention technology, speed humps, they're not just used in the UK, but widely, I think, throughout the world. Drivers hate them. You know, they harm the suspension, even for a user who's using the road in a perfectly normal way. It hurts the car. And it doesn't prevent someone from speeding. And moreover, when they do speed, it makes it more harmful that they're speeding on a bumpy road than if it was a smooth one, perhaps. So lots of problems. And yet we still use both these technologies. So we still inherently recognize as engineers and as decision makers that we need a technology like this. But if we think about transplanting this now into software, because we're dealing with a cyber technology, so once again we come into this world where software engineering is different. You know, we have cyber digital twins, which are inherently different to cyber physical ones. And when we talk about prevention for software, we're dealing with a technology which is inherently malleable, in which we can find incredibly subtle versions of these speed humps. So what we do is we have our bots, which are executing on the real infrastructure. They're being rewarded, say, now for crawling behavior. So they're trying to find a scamming victim, let's say. The victim in this case being another bot, of course. It's all entirely isolated and in a walled garden. But it allows us to deploy on top of those actions and observations that the bots engage in, various kinds of cyber equivalent of speed humps. So what we mean here is different kinds of ways in which we mutate or transform the actions the bots can perform and or the observations they can make. So without loss of generality, let's consider different ways in which we might rate limit the behaviors they can engage in. So for example, the rate at which they can send messages, the rate at which they can respond to messages, the number and size of messages they can send, these kinds of things, the number of other connections on the social graph they can see, the speed at which they can traverse from one to another. All of these things represent parameters that we can tune, and we can tune them with a constraint vector. So for example, this bot here can only send 4 messages a second, can only receive 12 a second, and can't see more than 17 connections on the social graph at a given time. So I made those examples up to illustrate, but I hope they give you a flavor. And then this bot has different parameter values for the same constraints. And then the third bot might actually mix too. So the second, it's got the same constraint on the number of messages that the bot can send as the first bot, and then the same constraint as the first bot on the number of messages can receive, and so on. I think you get the idea. This constraint vector could be thought of as a mechanism layer in between the bots and the infrastructure that controls how they behave. Could also be thought of as a simulation of possible candidate features that we might deploy on the platform. And thirdly, it could be thought each possible choice of constraint vector value could be thought of as a candidate for repair. But we don't need to recompile that entire infrastructure in order to execute these bots' behavior on the platform with that constraint vector. So we've now overcome the build time problem because we're not rebuilding the system. We have a mechanism layer that essentially simulates the effect of the changes we might implement. And changing the constraint vector is negligible time. We also have multiple bots, each of which can run a different value of the constraint vector, so we get incredible parallelism. We're simultaneously rewarding the bots for trying to achieve harmful ends, but if we now bring in a second community of bots who are just trying to achieve normal ends, there may be simulating new users on the platform trying to meet and make friends, we now can have a multi-objective problem where we simultaneously we find a constraint vector value which will simultaneously make it hard for the bad bots to achieve their goal, but will not hurt or even would improve the ability for the innocent normal bots to achieve their goal. So now We have a way to tackle the build effort problem, because we don't rebuild the system, we just change the constraint vector. We have a way to explore new possible features, because we just code those up as the anticipated effect they would have in the constraint vector. We can explore different interactions between possible features, because the constraint vector can contain an arbitrary number of elements, each of which simulates a different feature we might implement. And we can tune the behavior of these candidates that we haven't even implemented yet and their interactions using the simulation, which is on the real infrastructure, so we know it's giving realistic predictions of the behavior, and with realistic behaviors that we've seen for users, such as behaviors we prefer not to happen, like crawling and spamming, and behaviors that we do want to happen, like meeting friends and making friends for normal users. So the whole thing together becomes an approach grounded in simulation that tackles scale challenges and allows us to explore the space of possible features that might be deployed. And as you can imagine, these constraint vectors are quite large, and they denote a search space, and what we're searching for in that search space is a few subtle tweaks amongst an enormous space that will have these desired properties in a multi-objective optimization problem, where the objectives include at least enabling normal users to go about their normal use and inhibiting users with harmful intent. So, as you'd expect, when you're searching for a needle in a large haystack that is a search space, a natural technique to use would be search-based software engineering approaches. And that's essentially what we've been experimenting with in some of our more research-oriented work in the company, looking at how we use these kinds of technology to scale up genetic improvement ideas to search for candidate improvements to the infrastructure that will help make the platform as a whole safer. And if you want to read more about the overall approach that we use to simulation, we're currently using it for testing, safety testing, and for we've published a number of papers on this. But if you want to find the sort of one go-to paper that brings all this together, then I would recommend this one, which we published last year, I think it was. Cyber Digital Twins describes the whole approach and this hierarchy I mentioned, and how it balances that trade-off between speed and precision. And if you want to see about how what I've talked about today can be applied specifically to genetic improvement and program repair, then I've tried to capture that in this short position paper, which is the paper in the proceedings you have for your automated program repair workshop today. So with that, I'd like to thank you very much for listening to my talk today. I think there should be at least a quarter of an hour left for me to take questions and for us to have a discussion about these ideas. So with that, I'll hand back to the guests. Thank you very much.
Thank you so much. Yeah, we have time for questions. Okay, there is a question or comment from Wes Weimer. Is there a concrete Facebook meta example you can give of how a hierarchy of digital twins usefully manages the trade-off between precision and speed? I know you can't give all the details, but I'm curious about how it plays out in practice. I'll check out the E's paper in the background.
Yeah, so we do have a paper that talks about a particular case that we experimented with, where we're dealing with the kinds of behavior where a user with harmful intentions is essentially trying to misuse the platform and the fact that it has this tremendous connectivity. So they're using the platform to crawl over the platform, and they're searching for victims to apply scamming to. Now, that's a specific example I can give, we use in the paper, so it's in the public domain. I'm sure you can imagine how it would apply to other kinds of harmful behavior as well. And please just take my word that it can apply to those, but I can't talk so much about those, partly because we don't want to give away to people with harmful intentions the kinds of techniques we're using to thwart those harmful intentions, because that would obviously not be a good idea. But in terms of the scientific and intellectual questions about, well, how does the hierarchy help? So what we show in that paper is we consider a particular kind of rate limit where what we're trying to do is reduce the ability for a harmful user to misuse the platform, to essentially crawl over the platform. We've got to tension that against the fact that's what the platform's for. You know, we want new users to be able to find their friends, right? So that is a kind of crawling behavior too, right? But they're different, right? So on the one hand, the innocent crawling behavior is tending to hop from friends to friends and people that you likely know and so on, whereas the harmful behavior is really just trying to acquire as many contacts as quickly as possible. So you might believe that there should be some kind of rate limit that would limit the number of people you can see, the number of friends. If you're at a particular node in the graph, essentially the number of edges you can see at any given time, there might be a value you could constrain that to, such that these users still get to find all their friends, whereas these users don't get significant friction in terms of trying to, just acquire as many contacts as possible. And so we explored that in one of our papers. I want to stress, this is not something we've deployed. This is something we therefore can talk about in the public domain. It's in a paper. But we show how by then building a layer on top of that, where we have the online graph, where that's the real social graph, and we're exploring how that would work. But then we can build an offline version of that graph, and the offline version essentially captures what the responses would be, we anticipate, but it's not quite as high fidelity because it's running in offline mode, so it's not real anymore. And that's about 10 times faster than running on the online graph, but it's not quite the real graph anymore. And then on top of that, we can build an emulator to emulate so essentially a predictive model that would predict what the likely behavior of a bot would be in a particular scenario. And now we're not even having to run it on the graph. We can essentially squash the whole compute down to one predictive model computation. And that gives us several orders of magnitude scale up, but it is a predictive model. So now we are in the world where we've sacrificed the fact that we did have the real infrastructure, and now we have actually captured the whole real infrastructure in a kind of machine learned model that predicts how the real infrastructure would behave. But the nice thing is we have this ability to then keep going up and down that hierarchy. So we could go up the hierarchy, run a fitness function on a super fast fitness that's low fidelity but very fast. And then as we get fitter and fitter individuals, we can selectively try out lower and lower parts of the hierarchy to get faster. To get more high fidelity but slower fitness computations. So you can see how we would navigate that hierarchy. And this is described in one of our papers. I think it's the Ray's paper, Ray's keynote. I think it's this one. Sorry, I think it's the one I pointed to. The one I pointed to in the very final slide. Facebook cyber physical digital twins. If not, feel free to chase me, and I'll point you to the right paper. I hope that gave you a flavour, Wes. Do push back if it wasn't.
Yeah. So Wes said, "Thank you. The offline graph to predictive model example helped me get a better handle on it." Cool. Let's see. Other questions? Oh, so Sergey, you want to ask it yourself?
Yeah, okay, I will read myself. So what is your opinion about the problem with the low quality of automatically generated patches, something that sometimes referred to as test overfitting? So do you also see it as a instance of scalability problem, or it's something different, maybe even something having conflicting goals with scalability? And what do you think are the most promising directions to address this problem?
Yeah, so this is where I think scale is the solution, not the problem. What I mean by that is essentially what we're talking about. I hope I'm correct in understanding the question here. Let me just rephrase it as a handshake. So I think the problem is if my test suite is inadequate, which all test suites are in some sense, then the genetic improvement or repair technology can find a special case solution that passes all the tests, but that doesn't actually really fix the underlying problem. So another way of rephrasing the question is, how many tests or what kind of test suite would you need to really perfectly characterize your problem such that the only kinds of things that will pass all tests are correct solutions? Or could you have a test suite such that you pass it if and only if you're correct? And we know that theoretically the answer to that question is no. I mean, I can easily construct toy examples where you would need an arbitrary number of test cases to guarantee that no faulty program could go through the net. But isn't that what we already have in practice? If I'm a software engineer as a human and I land a change, then we run a whole load of tests. We have some humans look at the change, and none of those are perfect, and we have to make a judgment call as to whether to land it. You could argue that with repair, there's more propensity because the technology doesn't have all that human intuition to try to not circumvent, but will likely find corner cases. And there are some very interesting research questions on, what kind of tests are there that you would not, that essentially any technology would not would interpolate between these two tests. So if I pass this test and I pass that test, then essentially all the tests I could have imagined making in between I would pass. So for example, if I'm trying to repair a program that should add 1 to the input number, then I can make an arbitrary number of programs that are wrong on just exactly one value, but no genetic improver is likely to do that because it would have to make an extra if case just to capture the wrong behavior. So there is some very interesting research to be done on understanding where that continuity lies and what is likely minimal sets of test suites that would provide a decent safety net and so on. So all that's very interesting research. On the other hand, from the practical perspective, when we deploy at scale and we have enormous amounts of production data available to us that capture what we expect as normal behavior, and what we're essentially looking for is a regression. We're saying, did you fix this bug and not regress anything else? At least the piece is very well covered by the scale of the self. So I think that on the one hand, we probably are a little unfair on repair because we expect it to sort of be superhuman. And we accept lots of changes to software systems without adequate testing, and lots of human changes fix bugs and also have special corner cases that we missed and all the rest of it. And somehow we don't say we should stop humans writing software because it doesn't work. So that's one hand. The second point is, at least in the case of regression, we have a large amount of data. Scale is your friend there. But thirdly, I am still very interested in the fundamental research question about what are the kinds of test case that repair techniques will tend to evade, and how do we capture thinking of this test suite as a kind of a net, a semantic net that is very hard for the software to break out of. That is a really interesting research problem. I don't know if I've answered your question or just talked around in circles for about 5 minutes, but
yeah, thank you for your answer. Yeah, I understand your perspective about this.
So can I ask a follow-up question? I think this is related to what I had in mind. So I see Meta has deployed SAPFix and GetFix. They seem to fix a special kind of bugs, not the general bugs, like a lot of the generate and validate type of repair tools too. And as we talked about, there are various challenges, like the test suite, fault localization, and the time to run tests, for example. I'm just trying to see from your perspective, especially from industry perspective, what do you see are the blocking pieces for people to deploy those general repair techniques in industry? Do you see it wherever it would happen?
Well, I think that the biggest blocker, if there are blockers, I mean, I don't think there are any significant. I don't think there are any fundamental blockers. I think there are just practical inhibitors, let's say, not blocker. Blocker sounds a bit too strong. Right? So the biggest practical inhibitor would be the thing that Sergey was alluding to there, would be, well, I would want to deploy the techniques in a place where I've got maximum test coverage and maximum confidence in my testing. Clearly, that would be the natural, even if I just think of it as a prioritization problem, that would be the place to start in the priority order. And in many situations, there just aren't very many good, the coverage isn't that great. And so the testing community still has work to be done here to get more adequate system level tests. At the unit level, coverage is usually pretty good, but it's it's that sort of system level, do I dare deploy this thing? It passes all the unit tests, but if I miss some system level interaction corner case, and so system level coverage is probably the biggest inhibitor. On the other hand, as I say, I think that the scale gives us many potential solutions to that, because the scale means we have lots of system level tests in many organizations that will help us to be more confident. I do think that although it's been a subject of research for some 3 or 4 decades, the problem of automatically generating tests that can really cover what we're trying to fix with great certainty, that remains a partially solved problem. And if we had a solution to that, that would open the floodgates for repair and these kinds of technologies. So the two work hand in hand. But as I say in the paper, I think that looking at that the other way around, if we start trying to deploy repair and seeing how that highlights inadequacy in the testing, that can be a driver for automated testing research. So rather than saying, hey, let's wait on this repair agenda and not do any more research and wait until the testing's caught up, I argue we should go the other way around. We should say, let's drive forward this improvement and repair agenda, because it's the fastest way of showing up the inadequacies in our automated testing approaches in research and in practice. And that will therefore help us to improve those faster, which will bring all of our testing up a level with it. So it sounds like a slightly politician's answer, but the very problem with repair of this inadequate test is the reason why we should be pursuing it with such vigor, to try and clear up that problem, because it's not just a problem for repair. It's inadequate testing is a problem for the whole software industry and for the sector in general.
I see. What do you think of the limitation of fault localization then? Because a lot of times assume we have to know where the bug is. That seems to be also very difficult in practice.
Well, that's a very good point, Lynn. And I wouldn't say that it's not a problem in general, but what we can do, at least to make progress in practice, is we can pick specific cases where the localization problem is not so challenging. So the kinds of bugs that we've been able to fix so far in industry have been those where localization is relatively straightforward. As I mentioned in my talk, we use static analysis techniques to help us pinpoint the likely, and I think that's a very promising area of research as well. It's natural that in practice we'll be focusing on saying low-hanging fruit sounds a bit like we're kind of lazy, but we're not. What I mean is, if we're naturally going to focus on those areas where fewest of the problems still remain. So where we've got large test suites, where it's relatively easy to localize, because we still have all the other problems that you don't have in research. Like we have real developers who have to accept these changes, and they react in all sorts of ways that are fascinating in themselves, that I've talked about in the paper. But it surprised me that developers could see a fix that they could believe in, right? There was no question that it sneaked around the test or anything. They believe this is correct, right? And yet 50% of the time they will still commandeer that change and edit it themselves, and then because they want it their way, and that tells us a lot about the interaction between human nature and technology and all the rest of it. And I think it's an essential part. We have to have the human take responsibility. And if that means they want to rewrite it, they're best to know how the ongoing maintenance will be. But even in this very simple case of fixing a null pointer dereference, half the time they wanted to rewrite it their way. But the fact that they knew that this was a fix and they could start from a guaranteed fix is a much, much better place than just, hey, go figure. So I think your original question was about fault localization. I've managed to deviate way off, but I think there are plenty of bugs where the fault localization problem is not such a problem that therefore we can't do anything in practice. That doesn't mean it's not a problem in general, but it does mean we can, I see it as a conveyor belt. The research is trying to solve the general problem, and we're trying to squeeze out of that in industry some practical things we can apply right now. And by doing that, feeding back the results, then that means there's more that you can do at this end, and it's like a virtuous cycle. And in the end, we'll be able to repair everything. Well,
thanks a lot.
It'll probably be like the build problem. In 20 years' time, the things we'll be able to repair will be defined as trivial bugs. But today, they'd be defined as really tough bugs. Just as like the things that took 20 minutes to build 30 years ago were trivial now and could be built in seconds or microseconds. I would predict that in 20 years' time, we'll be fixing all sorts of bugs that right now we would think of: the localization problem, the inadequate test suites. All these would have been huge challenges. What will happen, therefore, is not that we say, hey, aren't we good at fixing bugs? We'll say, aren't these bugs trivial? exactly like it happens with games. You know, like once a computer can beat a human at a game, we just describe the game as trivial rather than the software as clever. You know. That's you.